Welcome to my channel, STEM Cafe, where we make everything science, technology, engineering, and mathematics interesting, easy to comprehend, to recall, to assimilate, and entertaining, fun. Today, we are studying rotational dynamics, and we can also talk about circular motion. I am happy, excited to handle this topic with you. I am Dimeji, and let's start. When we are talking about rotation, what are we talking about? We are talking about an object moving around a place, moving around a specific point. Today, we discuss about circular motion, really. And the ones we talk about is the motion around a specific point with constant radius and constant velocity. Constant radius and constant velocity, which means that it will describe a circle around this point O with constant velocity. But before we go into details with this topic, I want to introduce some terminologies to us. Now, we have a point as the center and radius r. If the body moves from this point to another point, at the center it will sustain an angle. Let's call that angle theta. If we want to measure this distance from here to here, what do? We calculate and say theta over 360 times 2 pi r. Let's call this place s is equal to s. That's what we do. What does it mean? It means that s is proportional to theta. That's what it means. S is proportional to theta. But when we are doing this kind of calculation, we don't always measure in the angle in degrees. We measure our angles in radians. We measure our angle in radians. Now, what is radian? 1 radian, or rad, is the angle subtended at the center to give s, which is equal to the radius. That is, when s equals r, the angle here will be 1 rad. Now let us find the value of 1 rad. So if we have theta over 360, this one is the degrees, times 2 pi r is equal to r. That is when this theta is equal to 1 r. So what do? 1 rad. So which means that for 1 rad, the angle will be equal to 360 over 2 pi. 1 rad. So which means that when the angle is equal to 360 over 2 pi, the angle is 1 rad, and that is what this one is. So we can say 1 rad is equal to 360 over 2 pi in degrees. Therefore, 2 pi rad is equal to 360 degrees. So this is what I'm trying to arrive at. So what do we now do? Anytime we are given angles in degrees in this situation, we must always convert it to rad. So if we are given an angle theta, let's say we are given an angle 5 degrees, I want to convert it to rad. The right thing to do is, we know that 2 pi rad equals 360 degrees. Therefore, alpha over 360 will be equal to k rad over 2 pi. So alpha will be equal to k will be equal to alpha degrees times 2 pi over 360. So if you want to convert from angle to rad, this is how you do it. You multiply by 2 pi over 360. That's another topic entirely. But what I'm trying to refer to as here is that the angle here is in rad. That's the one we use here. So what will our s now be? The formula for our s in terms of rad. This is in terms of degrees. In terms of degrees. So what will it be in terms of rad? So we have said that theta degree is equal to theta times 2 pi over over 360 rad. If you look at this, S is equal to theta over 360 times 2 pi times r. Therefore, if you look at this is the angle already in rad. So, and if we say this one is going to be K, if it's going to be K, so which means that our S will be equal to KR. That is, our K is angle in rad. I just gave this introduction because I realized that so many students might be confused or might have forgotten. Now, let us now go to our main representation of angle. So if our angle is given as theta rad, our S will be equal to theta r. That is what I am after. This is what I am really after. Therefore, we can now talk about angular velocity. You know, we have already talked, this is our distance. So, since the velocity is constant, this one we are discussing here now, we are talking about constant velocity and constant radius. But let us even talk about, before I get into that, let's talk about situation where our velocity varies. There are situations like that, but we are not dealing with that now. So here, if I want to talk about V is equal to S over T, and it will be equal to theta R over T. So if our theta over T, because here R is constant, if our theta over T is the change in angle by time, which we refer to as angular velocity, our V will be equal to WR. So W is angular velocity. So you take that now. So we have S equals theta R, V equals to WR. You can see there is a progression with change in time. W, theta, and now we can also talk about this as W over T, which is angular acceleration. We are not using this one now, but I just want to let you know that as we have the quantities in linear motion, we have it also in angular motion. So we have the angular velocity, and the angular acceleration. So in the same vein, we can also say if our initial angular velocity is W, our final angular velocity will be equal to WF, final angular velocity. This one is initial angular velocity. So we can now see final angular velocity is equal to initial angular velocity plus angular acceleration times time. Just like our linear whatever. We can also say WF all squared is equal to W squared plus 2 alpha theta. In the same pattern, we can also say theta is equal to WT plus half alpha t squared. So you can see, I just want you to see it like it's a very simple thing. Just follow this, it's done. Now let's go back to the main circular motion we are handling. In this instance, I want you to know that our angular velocity is equal to, is constant. Why? Our V is constant. Because our R is constant. So, alpha is 0. That is, angular velocity is angular acceleration, sorry. Our angular acceleration is 0. So, you can now continue. Now we have established that in this circular motion we are dealing with now, basic one, W is constant, V is constant, R is constant. So, we can also look at it like this. When we have motion from first Newton law of motion, first law, Newton, it says that everybody will continue to remain at rest or continue in a constant motion, that is constant velocity, in a straight line, unless force is acting on it. What does that say? It says that when there is change in direction, force is acting, and when the force is acting, it affects the value of velocity has changed. Hence, there is an acceleration. The acceleration is different from angular acceleration, please. The acceleration we are talking about here is about the one brought about by the force that is causing the body to change in direction. There is change in direction, but there is no change in velocity. Please take note. There is change in direction. There is no change in velocity. So in this instance, this makes it clear that there is acceleration. And towards which side? We are going to discover now. Where is the acceleration coming from? We will know now. Now we have this body like this. This is the radius towards this place. And we want to find the acceleration. We have v in this direction. You know our theta is in radian. Now, let us say we have this place, delta theta here. Very small, very small. And then the velocity here is also the same as v. But, you know, in vector, it puts direction and quantity into consideration. So, you now see v1 and v2. So, the acceleration, by the time you look at this place now, since this is tangent to the circle, this is right angle, and this one too is right angle here. What does that mean? It means that this place and this place will be supplementary, because the total angle in a quadrilateral is 360. So this place too will be 360, 180 minus delta theta. So which means that this place at the end of the day is going to be delta theta and go on a straight line. So this place too we have delta theta. Now, for acceleration, we are talking about change in velocity. Therefore, we can now calculate our v2 minus v1. Change in velocity is equal to v2 minus v1. Now, let me bring this, expand it, enlarge it. I have it like this. You can see. This is v1. This is v2. This one is delta theta. Can you see? But in summing, this is the horizontal. That's why I just put it here. Our v1, this is minus v1 now. Can you see? This is v2. From here, please, from this diagram, this is v2, this is v1. Looking at this and this place will be delta theta as well. That place is delta theta. Now, I have this as delta v, that is v2 minus v1, change in v. Please look at it. Since v2 and v1 are equal, I can just calculate my delta v here, because this is isosceles triangle. Let me bring this here. Can you see? So this is delta v over 2, delta v over 2. So from this place, I can now say delta v over 2 is equal to, this is v1 or v. Since v1 and v2 are of the same value, I can just say v1 sine delta theta over 2. v1 delta theta over 2, which is also v sine delta theta over 2. But mind you, when theta is small, when delta theta tends to 0, sine delta theta tends to 1 and tends to delta theta. When delta theta tends to 0, that is when it is very small, sine delta theta tends to delta theta. Therefore, I can now say delta v over 2, because it means that delta theta over 2 will also be very small, will be equal to v1 delta theta over 2, which is, that is, if I multiply by 2, therefore delta v will be equal to v1 delta theta, which is v delta theta. Please note, v1 is equal to v2 in quantity. v1, okay, let me write like this. v1 in magnitude is equal to v2 and is equal to v. So you can see we have gotten our delta v to be v delta theta. but v is constant. Therefore, acceleration is equal to delta v over delta t, which is v delta theta over delta t. You know, we have said that our v is constant, so this is the only bearing whatever. So, but you know, we have discovered initially that, okay, let me go. You know, we have said it before that delta theta over delta t is equal to w. So this acceleration is equal to v w, and you know v is equal to wr. So you can also say it is w squared r, and w is also equal to v over r. So you can say v times v over r, which is v squared over r. That is one of the quantities we are talking about now. So this A is constant all through. It's moving like this round. It's moving. So we now see the direction it is towards. If you look at this, let me grab this place. So looking at it from the initial diagram, this is delta theta here, v2, v1 goes in this direction. So minus v1 is like this, and this will be the relative velocity, the change in velocity. Now this place is delta theta. We say this place is delta theta 2, and by the time I do this, this one is like this. Looking at this place is perpendicular here. I say this is delta v here. What will this place be? What will this place be? This place here will be 90 minus delta theta over 2. That is what this place will be. So you can see this place, if you look at the calculation and from the diagram, it will tend to be 90 minus delta theta over 2. And if you look at it, delta theta over 2 is very small. Very small. Therefore, the direction of delta v here is towards the center. So that will be the direction of the acceleration. So this acceleration we are talking about here is towards the center. Why? If you look at this place now, and to v2, almost 90 degrees. That is what? It's almost 90 degrees. So you can see. So by the time this one tends to 0, this 90, that is delta theta over 2, tends to 0. 90 minus delta theta over 2 will tend to 90 degrees. In this instance, because we are talking in terms of radians, we will make this place pi over 2 minus delta theta over 2. Please, but just not to be too formal, I made it like this for clarity. So this, as this body is moving around, the acceleration is towards the center. And what gives us this force? What gives us this acceleration? Sometimes this acceleration will have to be brought in by the friction. If it is bike rounding a place, if it is by a string being rolled, the string will give the tension, the force that will hold this body round. So the body will feel like it wants to move away, but what the string, the friction, and whatever that's holding the body in balance will be the one to counterbalance the force that this circular motion is trying to overcome. That's what I'm trying to say. That's what I mean. Like, if you are rolling an object now, the string will be the one to be rolling it round, and it must provide the force to maintain the object in that circular motion. Else, the object will go away or move off in the direction of this acceleration. Move off in the opposite direction to this acceleration. So what is keeping it is that string. What is keeping it is that friction. And what is keeping it sometimes is that gravitational force of attraction. When we get there, we'll see. Now, let's look at conical pendulum. Conical pendulum. This is the pendulum. It's not really okay. It's just a deformation of cone by rolling an object round a horizontal circle using a string, a vertical string like this. This is a vertical string now, and when I want to use it to roll an object here, I will slant it a bit and then be rolling it here. I'll be rolling it here. So it will form a cone. At the end of the day, it will form a shape of cone. So that's why we call it conical pendulum. Now, what happens when I have an object like this? And so to the vertical, it must have an angle. Let's call this one theta. And from here to here, so this will be r, the radius r. And the tension here will be T. This is the object. It will have mass or weight. You have weight mg, mass m. And along this place, this tension in this place will be giving us the centripetal force. Please. And the centripetal force, that is the force towards the center, because the acceleration is towards the center. The centripetal force will always be equal in all situations as ma, which is mv squared over r, or nw squared r. Please take notes. So in this instance, our t is this. Therefore, we have mv squared over r, which is provided by the components of the tension along this direction. The components of the tension in this place along this direction, we provide this mv squared over r. Therefore, we can say t, this place will be theta. Can you see? Okay, let me draw out the force diagram. So I have mg, I have t, and I have theta. I have theta here. So this component must provide this. So let me make it to be like this. So this place will be mv squared over r. Therefore, mg equals t cos theta. Therefore, t will be equal to mg over cos theta. That's one. At the same time, mv squared over r is equal to t sin theta. You can see along this place. So let me now divide this one by this one. So I can say mv squared over r times 1 over mg is equal to t sin theta over t cos theta. So I can say this one is tan theta. This one cancels this. So v squared over rg is equal to tan theta. So if I know theta, I can find r, I can find any other thing. If I know r, if I know g, I know v or v squared, I can find tan theta. So all of this, you can use it to work whatever you want to work in this place. So in this instance, we have said the string here provides the mv squared over r, the centripetal force, the component of t along this direction. Now let's look at bicycle rounding a circular path. Now let's consider motion of bicycle rider round circular path. Let's say this is the circular path here now. As he moves round, there will be tendency of him to bend. Why? The centripetal force will be like trying to push him away. He will be feeling like he's being pushed away, but the centripetal force he needs is supposed to move him towards the center. That's why he's bending. And that centripetal force is provided by the frictional force at the heel of the bicycle. Now, we can now say F is equal to mv squared over r. You can see the direction at which F comes, because the bicycle will tend to be pushed outside. And r equals to mg. That's the points, that's the only points at which the bicycle is on the ground and it's not leaving the ground. So r should be equal to the mass times acceleration due to gravity of the man. Now let's take moment about g. Moment about g must be 0. That is, clockwise moment must be equal to anti-clockwise moments for balance. Else, it will be moved off or it falls off. Now, we can now see this one as anti-clockwise moments, and this one is clockwise moments. Therefore, clockwise moments is equal to anti-clockwise moments. So what do we have? Clockwise moment is F times H, and anti-clockwise is R times A. And if we put our theta, our angle here, please note, in this instance, the theta is against the vertical. In the previous one too, the angle is against the vertical. So we can now say F over R is equal to A over H. And if you look at A over H, you will realize that it is equal to tan theta. So what is our F? mv squared over R. What is our reaction here? Mg times 1 over mg. So tan theta. Therefore, tan theta in this instance too is equal to v squared over. So tan theta in this instance too is also equal to v squared over rg. That is for this situation also. Now let's consider the situation where the car is banking round. Now we see that the frictional force there is the one providing the mv squared over r. Now, if the force generated by this mv squared over r, if mv squared over r is greater than mu mg, sorry, from that leg of the bike, if this one is greater than this, skidding will occur. Skidding will occur. That is, mv squared over r is greater than mu mg. Skidding will occur. Now, let me divide both sides by mg. So I'm going to have v squared over rg greater than mu. And you know that from here, you have said that tan theta is equal to v squared over rg. So, when tan theta is greater than mu, skidding occurs. That is the condition. So, when this happens, the bikeman is on his journey to fall. Now, let's consider motion of car around a banked track. When you look at most of these roads, they are almost like saucer shape. So that when the cars are increasing their speed, they'll be going like they are going higher and higher by the side. So that is the reason, you see the reason why roads are constructed like that. Now, so if you have theta here, so please note, the theta in this instance is against the horizontal. This car is going straight. It's not moving down towards the side or upward towards the side. It's just moving straight. So we consider the reaction at this wheel, at these tires, as the only reaction at this place. We disregard the frictional forces for this when there is no side slip or strain. So, and the mv squared over r is provided by the side because it is balancing on the side. Now let's look at how the diagram of the force will be. Let's say r1 plus r2 is equal to rc. F1 plus F2 is equal to F2. Please, this T is for total. Now let me now draw the forces that is required in this instance. See this one now. We have this theta. You can see we have this theta here. So by the time you look at it, this one is perpendicular to this here. And this one is theta here. So this place is theta as well. So by the time you look at this one too, this place will be theta to this place. So here, the angle here will be theta. You can see the angle here will be theta. So this is RT. And we have mg here. We have mv squared over r in this place. But it's towards this direction. So I will put it like this. Because the component of RT here must give us mv squared over r. So you can see. So it is meter in this way now. I don't know this again. It is meter like this. So RT, you can see. So RT sin theta is equal to mv squared over r. RT cos theta is equal to mg. So if I divide this one by this one, I'm going to have RT sin theta over RT cos theta is equal to mv squared over r minus 1 over mg. So this one cancels this. So I have tan theta is equal to v squared over rg. So here too, I can easily get RT mg over cos theta. So that is what will happen. So what this shows is this: as the v square is increasing, the radius will be increasing to balance this one. Or as v increases, r2 can increase, and if it's not increasing much, then theta 2 must increase, or theta 2 must increase. That is why it is not straight. That is why it is curved up. You can see. So that along the line, theta 2 can increase. In case the rate at which v square is increased to meet up with the rate at which r will increase, they make this one also increase so that it will be balanced. Else, the car will jump over or roll over. So that is why it is saucer shaped. So that theta will vary along the line as it will be increasing. Now let's look at the situation where there is a slip. That is, the car, when it is moving, it moves with so much velocity that it is moving upwards. Let us consider what that will be like. Now, if there is side slip, it means that the car moves towards the opposite direction. And this F is now of very great importance. Which means that for the slight slip to occur at all, F must be equal to at least mu RT, coefficient of friction. F must be equal to at least mu RT. Therefore, this mv squared is, as I described the other time, is towards like this. So we are going to have r in this way again. As I described, this theta will be like this, RT will be like this, FT will be like this, and there will be theta here. And we are going to have mg here. You can see, we are going to have mg in this place. And we are going to have mv squared over r. The component here, like I said the other time, must balance this. Now, if we are going to solve this, for the slip to occur at all with this angle, we are going to have mg plus ft sin theta is equal to rt cos theta. Please note, we have this. At the same time, you can say mv squared over r minus ft cos theta is equal to rt sin theta. Now, let's make this n side subject of the formula. So I can say mg is equal to rt cos theta minus mu rt sin theta. Bringing this one, it should be rt cos theta into 1 minus mu tan theta. Then mv squared over r will be equal to rt sin theta, rt sin theta minus mu rt cos theta, plus please mv squared over r will be rt sin theta plus mu rt cos theta. Now, we should be equal to rt cos theta into tan theta plus mu plus mu. Okay, plus mu. And then what do I have? If I should divide this one by this one, I'm going to have mv squared over r times 1 over mg is equal to rt cos theta, rt cos theta into tan theta plus mu over rt cos theta into 1 minus mu tan theta. So if I divide, I'm going to have this, and this one is going to be tan theta plus mu over 1 minus mu tan theta. So you don't need to cram this. But I just want to bring something out. You know, from our knowledge of friction, tan phi is equal to mu, where phi is the angle of friction. Phi is the angle of friction. So if you input this here, mv squared, v squared, sorry, this one cancel this. So v squared over rg will be equal to tan theta plus tan phi over 1 minus tan phi tan theta. you can see that is the sum of two angles. It's going to be tan is equal to tan theta plus phi. That's what I'm trying to derive. So if there is slip, v squared over rg will be equal to tan theta plus phi. That is it. So you get that one. Now let's look at another situation. Now previously we have talked about horizontal circle. Now let's talk about vertical circle. Where gravity plays a very important role. Let's look at a motion round the center along the vertical, and we have the center here. It means that at this point, V, we have V in this direction. So towards the center, let us say we have a string here. There will be T here. And the body here, it will have mass N, weight mg. And this string here must also provide the acceleration towards the center, which means that T, because this one is against T, T is upward, this one is down, will be equal to mg plus, because it must provide that component, mv squared over r. So let's call this one T1 here. So let's now look at the different position. Let us look at different position now. Position 2 here. You will see that mg does not have any components along this direction. So T at this place will be equal to mv squared over r at the horizontal here. Let's now look at it at the topmost points. You can see at this place, T is also towards the center. Mg is towards the center. So you can see that T and the remaining T now must give us, the remaining portion of T must give us that mv squared over r. That is T3, if I call this place T3. And you can see mg is also downward. So the little portion that remains out of T3 must give us that corresponding part of the force that keeps this body in motion at this point. That is T3 minus mg plus mg, because the two of them comes down, must be equal to mv squared over r. So T3 must be equal to mv squared over r minus mg. So this T3, for this body to continue moving, it means that mv squared over r must be greater than mg. If it is lesser than mg, this body will fall down. If there is water in the bucket, the water will come down. So that is what happens. To keep the body in motion round like this, T3 at this point must be greater than 0. That is mv squared over r must be greater than mg. Now, let's now look at this. At this point, let's say this place is theta. What will be the value of T here? If you look at it, we have this mg. We have mv squared over r towards the center. Therefore, T theta, you can see theta here. So T theta must provide for mg. So, which means that this T theta must provide for mv squared over r. And at the same time, the portion remaining must overcome mg. So we have plus mg, if you look at it like this, cos theta. Because the component of mg along this place will be mg cos theta. So this T must provide for mv squared over r and mg cos theta. That is it. So at every point in time, so if you look at this, what is our theta in this place? Our theta here is 180 or pi. And what is cos pi? That's minus 1. That's what we have here. Look at this one. When it is 0, cos theta is 1. So at this point. So you can find the value of T, tension, on the rope at different points. At different points along the circle. Now let us look at it from the perspective of energy. So that we can know the minimum velocity that you can use to launch the body in motion so that we can have complete circle. Now let's try to get something. Now let's look at the situation where we have a body suspended from the center like this, and we just want to swing it once so that it will describe a full circle. What will be the velocity by which we have to project it to give us full circle, round full circle? Let's make this one the chord that joins it to the center. Oh. So here we will say we launch it with U, and let's make this point our reference point. Oh. So potential energy here will be 0, 2. And at this point, being that it comes down, this place will be minus R. So the velocity here is U. The potential energy here is minus mgr. This is mg. The kinetic energy here is equal to half mu squared. But please take notes. We know the value of t for each point. The value of t for each point will be m. Let's call this one theta. For every point, m t theta will be m v theta squared minus n g cos theta minus n g. Okay, let me see. It should be plus, please. Plus n g cos theta. Our t theta will be m v theta squared over r plus n g cos theta. Please take notes. And at this point, why did I put it like that? Because once I throw it like this, due to the gain in potential energy, the kinetic energy will be reducing, and the velocity will be reducing in the same way. Now, let's now get our point theta here. At this point, our u will be u theta. That is our velocity here, will be u theta. Our potential energy here, let's find what this distance will be. This place will be theta, and this is r. So this is r cos theta. So in this place, Ke is equal to half m u theta squared. Pe is minus r minus mg, minus mg r cos theta. And from the concept of conservation of energy, mechanical energy at this point, let me call this 1 theta theta. Mechanical energy be equal to potential energy plus kinetic energy is constant. Therefore, Pe1 plus Ke1 is equal to Pe theta plus Ke theta. Now, what is our, that one is minus mgr plus half mv squared, mu squared, sorry, is equal to minus mg r cos theta plus half mu theta squared. Now, what is, I want to make mu theta the subject of the formula. So I have half mu theta squared to be equal to half mu squared minus mgr plus mgr cos theta plus mgr cos theta. Now, if you look at t theta, that is t at this point, the tension here is mv squared, mv theta over r plus mg cos theta. So let me now make that. So t theta mu theta squared will be equal to t theta r minus mg r cos theta. Yeah. So if I should bring this one here now, I'm going to have half t theta r minus mg r cos theta is equal to half u squared minus mgr plus mgr cos theta. Please follow. Now, I want to make t theta r the subject of formula. In order to do that, I multiply 2 by 2. So now let me multiply 2 by 2. I'm going to have t theta r minus mg r cos theta is equal to, okay, times this one, no, is equal to n u squared, the initial velocity, minus 2 mgr plus 2 mgr cos theta. So t theta r will now give me nu squared plus 2 minus 2 mgr plus 3 mgr cos theta. Now, which means that at every point in time, if I just launch it with initial velocity u, this will be the theta r, or the torque. This will be the theta r. Now, at this point, as you have said the other time, t must be greater than 0. And we say that t was equal to v squared at this point. If we want to find our t at this point, we make our theta here 180, and that means that our t here must be equal to mv over r minus mg. So which means that this one must be greater than 0. So it means that our t theta r here must be greater than 0. So what does that mean? It means that u squared will be equal to t plus 2 mgr minus 3 mgr cos theta. And as I said, t must be greater than 0. So it means that mu squared must be greater, because if this was greater than 0, it must be greater or equal to 2 mgr minus, if this one is minus 1, cos theta is minus 1 here, plus 3 mgr, cancelling n. It means that u squared will be greater or equal to 5gr. So what does that say? That means if I want to launch it, and for the body to circumvent, navigate full circle, u initial velocity must be greater than or equal to root of 5gr. Please, I just introduced this so that in case you come across any trickish question, we'll know how to handle it. In this instance, we are not handling the rope. We just throw it round, we just throw the object and it moves on its own, attached to the center. But there's another one. The initial one I did was when you are holding the rope and you swing it round, at every point in time, the velocity is equal. In this instance, the velocity is not equal throughout. It is varying. You can see, as it is gaining height, the velocity is reducing. Now let's continue with our rotational dynamics. In this section, what we are talking about is about rigid bodies. And from our past lecture, we have talked about rigid bodies. They have what? Fixed dimension. That is, they are not expanding or contracting. So hence, their dimension is fixed. Their dimension is fixed. The size is fixed. Now, which means that the fixed body, the rigid bodies, is combination of multiple particles. And if you want to find anything about their motion along the circular path, you can't just take it like, oh, this is the whole mass, this is the whole size. There are some other things you have to put into consideration, and that is where we talk about moment of inertia. Moment of inertia. So, and from basic mechanics, we have said that inertia is the tendency of a body to continue in state of rest or motion. That is, it will resist coming to rest. if it is in motion already in a straight line. So moment of inertia is also about resistance of rotation or resistance from being stopped when it is already in rotation. So it is the tendency of a rotating body to continue in its state of rest or rotation, that is, resists motion when at rest and coming to rest when in motion. So that is our moment of inertia. Our moment of inertia is just like a moment, that is distance times force. At the end of the day, that's how it will look like. But this is just moment of inertia, and I will tell you how we come about it in this section. The quantity moment of inertia is very useful when we are talking about kinetic energy of rotating body. Now let's look at a body. We are trying to rotate it along the horizontal circle, like this. We are trying to rotate it like this. You know, the height is the same all through. So we have it like this, and we are rotating it like this. So we can talk about only the kinetic energy in this situation. Fine. Now, let us now say this is how the body looks like, and we have fixed it around this place. We are now trying to rotate it. For each particle, let us take particle 1. The mass of the particle 1 will be m1, and let's say the body is rotating with angular velocity w. Angular velocity w. Let's say the distance of mass m1 from the fixed point is r1. Another body, let's call this one m2, and the distance is r2. Another one here, let's call it m3, and the distance r3. So when we want to calculate the kinetic energy of each of them, let's calculate Ke will be equal to m1 times v1 squared half plus half m2 v2 squared. You know, w is constant for them, but the distance from the axis of rotation differs. So that's why we are having different velocities. You see, plus half m3 v3 squared plus like that for all the particles. Now Ke will be half m1 w r1 squared. You know, our v at any point in time will be wr plus half m2 wr2 all squared plus half m3 w is constant r3 all squared plus like that continuously. Then by the time you look at it, w is common, half is common, so Ke kinetic energy will be half w squared is common to all of them. W squared is common to all of them into m1 r1 squared plus m2 r2 squared plus m3 r3 squared, and continues like that. So Ke at the end of the day will be equal to half w squared summation m1 r1 squared. So it's always referred to as second moments about certain points. Second moments, that's because it has r squared here. So it's similar to variance in statistics or Yes, variance and standard deviation in statistics. So that is what we call, so summation M1 R1 is what we R1 square is what we refer to as moment of inertia. It's what we refer to as moment of inertia. And that brings up another quantity. We call it radius of gyration. Radius of gyration. It should be equal to square root I over n. Square root I over n. So that is what will give us this. Now, the knowledge of calculus helps us to calculate moment of inertia for different bodies. For this class, most times you are not tested on calculation of moment of inertia. They will give you most times. That's one. Or they will give you a section that you can easily get what you are asked to find. So we look at the formula to get all the other ones. But before then, let's look at how to get moment of inertia of circular shape and straight wood, straight objects. Now let's look at how to get moment of inertia for uniform rod. Moment of inertia for uniform rod. Now let's calculate moment of inertia about the midpoint. The midpoint, which accidentally is the center of gravity for this. Now let's have this like this. Sorry about my drawing. And let's make this place to be the center. Now, if I take one small part here, the mass of this, and let me call this place x, and the length of the object is L. The length of the object, is L. So this place will be L over 2, and this place will be L over 2. Now, what is N? Mass is, let's say, density times area times L. That's the whole mass times total length. This area, so this is area density. Now, what is the area of this small part? This place will be delta A, and this is delta X. Delta X T. Delta X T. That is the area here. What is the mass of this place? Delta N will be equal to N over L times delta X. Yes, because it's proportional to the thickness here. Now, what is the moment of inertia of this place to this place? Moment of inertia is going to be moment of inertia will be equal to dn times x squared. So the moment of inertia of this is x squared, that is the distance of this place to this place. Is x squared dn. So if you now take the moment of inertia of everything now, we are now going to have moment of inertia of the rod will be equal to from L over 2 to minus L over 2 x squared dn. This one. And so what am I going to have? This will be equal to L over 2 to L minus L over 2. I'm going to have n. What is n? Okay. dn. N over L x squared dn. So I put it here, x squared dx, and it's going to give me m l x cubed over 3 from L over 2 to L over minus L over 2. So what does that give me? Let me impute L over 2. So I'm going to have m over L over 3L into, this is going to be L cubed over 8 minus L cubed over 8 plus L cubed over 8. And it's going to give me m L cubed over 12. Because this is going to be L cubed over 4. So it's going to give me m L cubed over 12. So you can see, it's very interesting. Just know what you need. Which means I don't even really need this in the first place. So this is what I need. Since it is proportional to the length of the object. So see, I don't need it. I don't even need this again. So m is proportional to the length. So m dm is dx, ml dx, m over l dx. So that is to find the moment about the midpoint. Now let us find the moment about the edge, one of the edges. Now let's find moment of inertia of a uniform rod. Moment of inertia of a uniform rod. Of a uniform rod. About its midpoint. Its midpoint. And about one of its edges. Now let's do this one, just to show the simplicity of getting it. If we have a rod like this, uniform rod, and this place happens to be the midpoint. You know the midpoint is also the center of gravity for this one, accidentally. Note, not always will the midpoint be the center of gravity, but because it's a uniform rod, that's why. Now, if the mass of the rod is equal to m, length of the rod is equal to L. So if we are going to look at it, from this place to this place will be L over 2. And from this place to this place will be minus L over 2. Now, let us take small elements here. Small element here with length delta x. So the second moment of the element about the center will be equal to m x squared. Mx squared. Now let's find what is m. M over L will be equal to n over delta x. Okay, I call it dx. M over dx. Therefore, n will be equal to m dx. This is capital M, please, over L. I'm trying to differentiate this small letter, this capital letter, please note. This one too is small letter, and this one is small letter. Now, so I will be equal to summation of different second moments of the elements about this point. So I'm going to have I to be equal to m x summation mx squared from L over 2 to m minus L over 2, and this should be m x squared dx over L from L over 2 to minus L over 2. So on integration, I'm going to have m over L into x cubed over 3 from L over 2 to minus L over 2. And what does that give? It's going to give me ml into ml over m over 3l into L cubed over 8 minus L cubed over 8, that is plus L cubed over 8, which will be m L cube over, this is 4 now, 12L, which will be NL squared over 12. You can see. So it's very easy, and just for you to understand it, even if you are not given, you can easily get it. Now let's look at it about this edge here. Just for you to know that it will not be the same on the rigid body throughout. It will vary from place to place. As you move, when you want to get moment of inertia about the center, it will be different from when you get it from 3/3. It will be different from when you get it from the whole length of the rigid body. Now let's look at it about one of its ends. Let's make it one of its ends. So it will be like this. And about this point. So let me take the elemental particle here, and this is dx. Fine. So the whole mass, this is L. N is the mass of the rod. L is the length. So mass of the elemental, mass of elements will be equal to N over L. Yes. Now let me take the second moment of this about this point. So second moment about end will be N x squared over L dx. So moment of inertia of the rod about its end will be equal to summation from L to 0. So you can notice the initial one was from L over 2 to minus L over 2. But in this instance, it is from L to 0. So I'm going to have N x squared dx over L. And that will give me N over L into x cubed over 3 from L to 0. So you can see. So that one gives me M L times L cubed over 3. This one gives me square. So it's giving me N L squared over 3. You can see it's very easy, straightforward. Very easy, straightforward. So in this instance, I have this one as M L squared over 3. And radius of gyration, K, is equal to root of L squared over 3. This one is K is root of L squared over 12. So that's it. So at every point in time, you can easily get it. And if you are interested in getting more, integration is done under application of integration. So you get it there. Now let's talk about the relationship between moments of inertia about CG and parallel axis. What we are trying to say here is, if you are given moments of inertia about CG, about center of gravity of an object, you can find the moments of inertia about any point parallel to the center of gravity. That's what you are saying. So this one is equal to IG. Now, if you have this object like this, you can see, and if this is the G, and we have a point, we want to calculate it about this point. Let's call this point H. The distance of this place from G, let's call it small h. Now, let's take a particle here. The distance from this H now, and distance from G. If the distance from G is x, the distance from H will be H minus x. You can see. Now, let's call it mass m, small m. So the moment of inertia of this point. Now, second moment of this particle about H will be about H will be equal to m into H minus x all squared. Because x is what is used to find the moment about G. Now, for the whole body now, moment of inertia about H will be equal to summation n into h minus x all squared. And that will give me summation n h squared plus summation n x squared minus 2 summation n h x. Therefore, this one, h is constant. You understand? The only variable here is x. We are going to have, what is summation n? Summation n is equal to the mass of the object. It's going to be n h squared. And from our knowledge, we know that summation n x squared is the ig. Moment about g. And for this one, we are going to have minus 2h, because h is constant. Summation n x. And about the center of gravity, summation mx will be equal to 0. Summation mx is equal to 0. How? Remember moments. All the moments about center of gravity, moments about center of gravity, about CG is equal to 0. So that's what we have here. Therefore, moment about H, parallel to X is equal to n h squared plus I g. So if I want to find the moment of inertia about this point, I am given the moment of inertia about g. All I just need is to add this moment of inertia to mass times the square of the distance of this place from the center of gravity. Now let's look at this relationship between moments of inertia about perpendicular axes. Let's talk about if we have axes x, y, and z. X, y, and z. Okay. And let's see, I have something like this. And I want to find the moment of inertia of this particle about this place, about OZ. This is the object, about the perpendicular axis. You know, this is R here. And this one here will be this here. This one will be the component of R about X, about Y, and this one about X. So this place will also be OY, OX. You can see. So this is R1 and M1. So if I have it like this, the moment of inertia about Z, about OZ, moment of inertia about OZ will be equal to M1 R1 squared. M1 R1 squared. So, or let me just say second moment of this mass. So moment of inertia of, and this will be equal to, if you want to break it into components, it will be n1 x1 squared plus y1 squared. So you can see, therefore, moment of inertia of the body about OZ will be equal to summation n into x1 squared plus y1 squared. So what does that mean? And we should be equal to summation n x1 squared, x squared, sorry, summation n x squared. Summation is going to be n summation n x squared plus y squared. And this is going to be summation n x squared plus summation n y squared. And what does that mean? Summation m x squared is the moment about the OX axis, and the summation m y squared is the moment about second moment about OY axis. So it's going to be IY IX plus IY. So if I know the moment of inertia of this body about X axis or about Y axis, the summation will give me the moment of inertia about Z axis. And if I know the one of about Z axis, I know about Y axis. I can know that of about Y axis. If I know it about Z axis and X axis, I can know it about Y axis. It will just be IZ minus IX will be equal to IY. So, and this one is IZ. So that is all about moment of inertia. So for interest sake, Just go and study it more under calculus integration. Now let's look at torque on rotating body. Torque on rotating body. Let's say we have a body like this, and we have torque acting on it here. So if it is rotating about this point, and we have a particle mass m1, the force on this mass m1 when it is rotating is F is equal to m1a, and the torque T1, the torque here is equal to F1 R1, which is m1 a r1. Now, if you look at A, in this instance, the A is perpendicular. You know the torque is perpendicular to the distance from here. So, this F is also perpendicular. Therefore, the torque is also perpendicular. Now, this A in this instance, since it is perpendicular, is going to be dv dt, which is equal to V. And what is our V? D WR dt. So for this one now, we are going to have d r dw dt. Here dw dt is equal to alpha. You can see. So our T1 is equal to m1 r1 alpha times r1, and T1 here is equal to m1 r1 squared alpha. This I hope you follow. The force on this body when it is rotating is m1a along the perpendicular to the distance from the axis of rotation. So T1 for this body is going to be f1 r1, which is m1 a1 a r1. So this a for this body, okay, let me make it a1. This a1 for this body is dv dt, and we know from our previous section that v is wr. So the wr dt, and so this r1 is constant in this instance. So we have r1 dw dt. So the w dt is equal to alpha. So T1 is equal to m1 r1 alpha. This is the a. This one here. So the total torque on this mass now is T1, which is equal to m1 r1 squared alpha. That is the torque on this body. Now the overall torque on the whole body, T is equal to summation m r squared alpha. And remember, our summation m r squared is equal to I. And so our torque is equal to I alpha. So when torque is acting on the body, there is moment on the rotating body. There is the angular acceleration. Please note, alpha is angular acceleration. Remember, if you compare it to that of linear motion, F is mass times acceleration. In this instance, we consider torque, it's rotation. Moment of inertia times angular velocity. So that makes it easy for it to stick in the brain. No, alpha is same for all particles. That is it. So we talk about, now let's look at work done by torque or couple. Work done by torque or couple. So what happens is this: F work done is equal to F times distance, and in this instance, our distance is r theta. Remember, for this is the distance, circular distance traveled, r theta, since theta is measured in radians. So, and this one will now give us Fr into theta. Remember, our Fr is T. Fr is equal to T. So, work done is equal to T torque times theta. So if you have what's it called? The moment of inertia, and you can find the angular acceleration, you can easily get the work done. It depends on whatever formula you want to use. Everything is similar to linear motion. So the formula for the work done is T theta, where T is the torque or curve, depending on what you want to call it. Now, for the kinetic energy, we have, that's what we use to open the topic. We say it is half I W. We derived that initially. Now, for angular momentum, if you have a body like this, and this particle is rotating, and the angular velocity is W. So the velocity of this body, let's call this one M1, and the distance from this place is R1. So the velocity of this body here, V, is equal to R1W. R1W. The momentum will be equal to N R1W. Now, the how do I put it? The moment of this momentum about this place. Moment of the momentum about the axis will be equal to N R1W times R1, which will be equal to NW R1 squared. So the moment of the momentum about the axis is M1 R1 W times R1. M1 W R1. That is the moment of the momentum about this point. Now for the whole body, if you are going to do that, for the whole body, moment of the momentum will be equal to summation M1, summation M R squared W. You know W is constant, and M and R varies. So we are going to have W summation M R squared. And you know this M R squared is equal to I. So I'm going to have I W. That is the angular momentum. Angular momentum about point of rotation. Point of rotation is equal to I about the point times W. Now, in this instance too, we also have the momentum conserved. Angular momentum is also conserved if there is no external torque about the point of rotation. So, let me put the law of conservation of angular momentum. Angular momentum is conserved for a body or group of bodies about a point, unless external torque is applied about point of rotation. So that is it. So in this instance too, angular momentum is conserved about the point of rotation. So now let's look at it. Law of conservation of angular momentum is very similar to that of linear momentum. The angular momentum about an axis of a given rotating body or system of bodies is constant if no external torque, acts about that axis. So which means that if there is rotation taking place and no torque is acting on the body, even if you introduce any body on it, the angular momentum is maintained. When we get into calculation, you will get that one better. So that is why when a swimmer rolls when it folds himself or herself to be smaller, it can roll more times because the I has reduced, and it can roll faster and roll more within short time due to the conservation of the angular momentum. So you will see more applications when we are doing the calculations. So that is why divers when they are trying to enter, the pool, when they roll, when they are still stretching, when they are still a bit stretched, they will roll fewer times. But when they've called more, they will roll more times before they get into the water. Why? Their moment of inertia has reduced, and the angular momentum must be maintained. So they will continue faster due to that calling and reduction of moment of inertia. Of the formulas and comparing the linear and rotational motion. Velocity is v. We talk about angular velocity mainly in rotational motion, but we know the relationship v equals to wr. That one is sure. Momentum, the one we talk about in linear motion is momentum, mv, mass times velocity. Angular momentum in rotational energy, that is moment of inertia times angular velocity. Thirdly, we talk about kinetic energy in linear motion, and that is half mv squared. Here, the rotational energy is the kinetic energy there, and it is half I w squared. I is moment of inertia, w is angular velocity. Acceleration in linear motion. Angular acceleration, alpha, in rotational motion. And you know the relationship here. A equals to alpha r, just like v equals to omega r. Here we talk about force, and that is ma. Force is ma, mass times acceleration. Here we talk about torque, moment of inertia times angular acceleration. Moment of inertia times angular acceleration. And we also know the relationship between torque and force. Torque is the force times perpendicular distance. We also talk about work done, that is force times distance in the direction of the force. And in rotational energy, work is torque times angle. Torque times angle that is moved through. We also talk about conservation of linear momentum on collision in linear motion. Here, if no external forces applies, and we talk about conservation of angular momentum on collision if no external torque. You can see momentum is conserved here, linear, here, angular, but here, no torque, here, no force. So with this in mind, we will now do some examples to show you the mindset you should have whenever you are handling any problem under rotational dynamics. There is similarity between the two of them, but the quantities you put into consideration are a bit slightly differ. So that's what we are going to do now. We have this question. It says the moment of inertia of a solid flywheel about its axis is 0.1 kilogram meter squared. It is set in motion by applying a tangential force of 20 Newton with a rope wound around the circumference. The radius of the wheel being 0.1 meter. Calculate the angular acceleration of the flywheel. What will be the angular acceleration if a mass of 2 kg were hung from the end of the rope? Let's make g acceleration due to gravity 10 meters per second squared. Now, what we have is this. We have a flywheel. It is hung like this, and a force is applied here. And we are told that the force is 20 Newton. And this R is 0.1 meter. The moment of inertia, I, is equal to 0.1 kilogram meter squared. Now, we have to find the calculate the angular acceleration of the flywheel. Due to this force now, we can calculate our torque. T is equal to 20 times 0.1, which is 2 Newton meter. And we have already proved it, or showed it, that T equals to I alpha. Here I is moment of inertia, alpha is angular acceleration. Angular acceleration. Therefore, 2 is equal to 0.1 times alpha. So alpha will be equal to 2 over 0.1, which is 20 rad per second squared. So that is very simple calculation. Now we are also told that what will be the angular acceleration if a mass of 2 kg were hung from the end of the rope. Let's see how it goes. Now the major thing is, I'm trying to emphasize this. Just look at the procedure. Very simple. We are told that instead of that force, it is replaced by weight. And we have to find the angular acceleration. I want you to look at it very well, the way it will be done. It's very simple. So our weight is 2g. Now, if this body is coming down, we have said that inertia, moment of inertia, is like resistance to rotation. Therefore, we have this here now. See, F, let me call this place F. And F will come down like this. So F will be the resultant force, the force that will now act, that will give us the torque we need now. This force will be the one to pull it down. And this force is also acting against the weight. So let's look at how it goes. See now, the torque will now be equal to F times R. And we know what our R is. And this torque at the same time is equal to I alpha. Remember, please follow. Fr, T equals Fr, which equals to I alpha. Now, this F is now acting against this 2g. Therefore, the acceleration downward for this one will be, we know that F is acting against the 2g. So, mg minus F equals to ma. And we know what our I alpha is in this place. Therefore, we can know what our F is. F will be equal to I alpha over R from this place. I alpha over R. So I can bring this one inside this place now. So I can now say mg minus I alpha over R equals to ma. Since we are calculating angular acceleration, I can convert this one to angular acceleration to R. A equals to alpha R. So let me substitute this in this formula now. I can now say mg minus I alpha over R is equal to m alpha R. So mg minus I alpha over R equals to m alpha R. Since I'm trying to find alpha, let me bring everything that contains alpha to this side. So I can say, since this one contains R here, let me multiply through by R, or I can divide through by R, anyhow. So I can now say mg R minus I alpha equals to m alpha R squared. Let me bring this one to this side. So I can say mgr is equal to m alpha R squared plus I alpha. Then, let me factorize this side. I can say mgr equals to alpha into m R squared plus I. Therefore, alpha is equal to mgr over m R squared plus I. So from here, I can calculate the acceleration. I just multiply this one by R. That's the acceleration of this one. And then, if I should consider the time taken, or if I know the distance, I can find the velocity. I can find so many things right from this. So this one is gone. Just consider, make sure you put every force into consideration, and every force and torque. The first thing, go for the torque. Check the forces, and then you consider all the other motions taking place. Translational and rotational. Now let's look at another way of doing it. Now another way of doing it is to consider the energy involved. Energy involved. In this place, we have W here, the angular velocity. And let's consider, if this one rotates, this one will move. Let's consider the distance moved to be equal to h. Let's consider the distance moved to be equal to h. Just give it a hypothetical distance. Now, the potential energy at height h for this one is going to be PE is going to be 2GH. That one like that. And now, if it gets down and it touches down, the kinetic and rotational energy of this will be, so on touching, on N touching ground, total energy, that is kinetic plus rotational, will be equal to PE. That is, this energy would have been converted to kinetic and rotational energy. So what should that be then? We are going to have, therefore, 2GH will be equal to half mv squared plus half iw squared. You have gotten that. Half mv squared plus half iw squared. Now, since we have gotten this, now our distance from here to here is h. So the PE for this one now, PE, potential energy, is equal to mgh. Yes, let's put it that way, mgh. When this body touches the ground, it will have moved and gotten certain velocity, and this one will have gotten certain velocity, angular velocity. So we are going to have something like this. Total energy on m touching the ground is equal to Ke plus rotational energy, kinetic energy and rotational energy. So what does that mean? It implies that mgh is equal to half mb squared plus half iw squared. Remember, so that's what we are going to have. The kinetic energy of this one and the kinetic energy of this one will be equal to this, due to conservation of energy. Now, let's now, but we know that W equals to V over R. So let's substitute this in this formula. So I'm going to have mgh is equal to half mv squared plus half iw iv squared over r squared. Now let's multiply 2 by 2 for e. So I'm going to have, let's multiply 2 by 2 r squared. Let me put it like that. Multiply 2 by 2r squared. So I'm going to have mgh, 2mgh r squared is equal to m r squared v squared plus I v squared. I multiply 2 by 2 r squared. So this one has 2 here. Now, since I know what v, I can factorize this side now. I can now say 2 mgh r squared is equal to v squared into m r squared plus I. So v squared is equal to 2 mgh r squared divided by m r squared plus I. You can see, whereby m r squared plus I. But we all know that for distance, we know that v squared equals u squared plus 2ax for the linear distance down. Our u is 0. A is what we are going to find. S equals to h. Therefore, v squared equals to 2ah. So this one is going to give us 2ah. So therefore, we can say 2mgh r squared divided by m r squared plus I is equal to 2ah. So let's pause. Therefore, I have mgr squared over mr squared plus I is equal to a. And we know one thing, that alpha is equal to a over r. Therefore, alpha in this instance will be equal to mgr squared. Okay, let me put it here. So alpha is equal to a over r, which will be equal to mgr squared divided by mr squared plus I times 1 over r. You can see that is a. This one is a. So I am now dividing it by r. So alpha is equal to mgr over mr squared plus I. just like what we got in the other place. So this is what I'm trying to show you. Now when you consider the energy and when you consider the forces, the one that you are inclined to, you will get the answer straight off. Now we will now substitute what we have here to get our alpha. So alpha, what is our N? 2. What is our G? 10. What is our R? 0.1. Divided by 2 times 0.1 squared plus we have our I to be 0.1. And that is going to give me 2 divided by, let me find that out. So this one gives me 16.67 rads per second squared. So you can see, anyhow you do it, you get your answer. Now let's consider the motion of a body rolling down an inclined plane. We have it like this. And we have the rolling body like this. It has moment of inertia I. And it has mass N. Ng. And when it rolls, there will be a frictional force towards the side. F. And it also has a radius R. The component of Ng along the plane is going to be Ng sine theta. So if you have theta here, that's it. Now, we want to now consider finding the acceleration. You can find the acceleration of the body if you have constant acceleration down. You can do it by considering the forces, or you consider the energy involved. Now let's look at it. If you consider the forces, the force F here, when the body is rolling, it will be giving it torque. It's the one giving it torque. So what do we have? Fr, T equals to Fr. The force, the frictional force times the radius, and that is giving us I alpha. That's giving us I alpha, and we can also say it is I A over R. I A over R. That is the torque. Now, if you consider this force here now, you can see that we have mg sin theta here, and we have F acting in the opposite direction. So the resultant force along the plane is going to be mg sin theta minus F, and that will give it translational acceleration down the plane, which will be equal to ma, and that is giving us ma. So if you want to find a now, you can do it like this. You can say mg sin theta. Let's find what F is here. F is equal to IA over R squared. So we have mg sin theta minus IA over R squared is equal to Ma. You can see. So from there, I can now say mg sin theta is equal to Ma plus IA over R squared. Therefore, mg sin theta is equal to A into N plus I over R squared. So simple. A will be equal to mg sin theta over N plus I over R squared. So that is the acceleration down the plane. You can find the velocity here at this point or at any point. How do we do that? V, let's call the distance down like this, S. So we can say 2AS is equal to V squared. 2AS is equal to V squared. So we can find V here, we can find W here. Even we can find angular acceleration. We just divide this one by R. Simple. So let's look at what our V will now be. So we are going to have 2. So V squared will be equal to 2 mgs sin theta over n plus I over R squared. So you can see. So yeah. So you know what our V is now. Just to square root this one, we get our V. And once we know our V, we can get what? Our angular velocity as well. So V equals to omega R. A equals to alpha R. So if you get A, if you get V, you can find all these other ones. Very straightforward. So whenever you are just handling any of these questions, just consider all the forces, the torques, and the velocity or acceleration at every point. Now we consider this from force perspective. Now let's look at it from energy perspective. From this place to this place, we call it H. So potential energy at this point, P is mgh. So if this rolls down to this place, we are going to have kinetic energy plus rotational energy. And at this point, total energy at the base is equal to half IW squared plus half mv squared. So due to conservation of energy, the energy here will be equal to the energy at this point. Therefore, we have mgh is equal to half IW squared plus half mv squared. Just like we did the other time. Let's try to make this in terms of v. All these ones here in terms of v. So I have mgh equals to half I v squared over r squared plus half mv squared. And you know, we have already known that w equals to v over r. So then let's multiply through by 2. So I have 2 mgh equals to v squared into I over r squared plus n. So from here I can find my v squared straight. So v squared equals 2 mgh over I r squared plus n. Straight. So we know what our h is here. H is equal to s sine theta. S sine theta. So we have, so it's going to be, it's going to be 2 mg s sine theta over I plus n. I over r squared plus n. So you can see the expression now. So straightforward, you can get it now. And we also know that v squared equals to 2as. So v squared from this place. So we can find our a. And let's see how it goes. So 2 mgs sine theta over I over r squared plus n. This is our v squared. Is equal to 2as. Now let's put the common thing there. So our a now is equal to mg sine theta over I over r squared plus n. So from here we can find our omega, and from here we can find our alpha. Very straightforward. By the time you compare the two, you see that we came back to the same answers. So that has proven to us that it is very simple. Just make sure to know what you are looking for. Now this is to perform experiments for measurement of moment of inertia of flywheel. What do? We attach a weight here and we allow the weight to go down. When it touches the ground, we measure some things. Number one, we will count the number of tons of this when this one goes down. So we count how many number of tons the flywheel rotates before it gets down. And after it gets down, how many number of tons before it comes to rest. So let's call that one n. N is number of tons from the drop of n till it touches the ground. Now, n1, let n1 be the number of tons after n touches the ground till the rotation of the flywheel out. You will see, till the rotation of the flywheel out. Now, we also count, so we have counted the number of tons. So we need to take the time, T1, time from for N1 to take place. Let me make it like that. Time for N1 to take place. So if we have known the time, this one, if we can calculate it, we count the number of turns, and that one, everything is okay. Now, we will now consider the energies of the bodies. We will now consider the energies of the bodies. Now, we know what N is now. We know our G. We know what this is, H. You know what H is. And you know this H will also determine the number of turns, whatever. So, we know what H is. We know this number of turns. And then, let's start. If any other thing, we are trying to find I. We are trying to find I. So, at this point, mind you, when this body is rotating, there is frictional force that will take away part of the energy of this one. So, the frictional force per rotation will be F. So please take notes. F will be frictional force. I said frictional force. Frictional energy lost per rotation. Please take notes. Frictional energy lost per rotation. So NGH now, the potential energy, NGH will be equal to, when this one touches the ground, will be equal to half NV squared plus half I W squared plus NF, because this is the number of rotations that will take place before it gets down. So plus NF. That is, let's make this one 1. Now, after it touches the ground, it rotates like for some times, for N1 times before it stops. Which means that this IW here will be converted to the frictional energy. The frictional energy will resist it until it stops. So therefore, since we don't know F, we can now say the energy half I W squared will be equal to N1 F. So we are trying to get F in terms of W to substitute here. Therefore, we can now say F will be equal to half I W squared over N1. So we can now put it here that MGH will be equal to half M V squared plus half I W squared plus half I W squared over N1 times N. You can see this N is still back here. Therefore, MGH will be equal to, okay, let's multiply 2 by 2. So 2 MGH will be MV squared plus I W squared into 1, please. 1 plus N over N1. So from this, I can factorize and find I. From this case, I can factorize and find I. Now, let's now see how to get what our W is. To get our W, you know the average velocity for this flywheel after this one has touched ground. The initial velocity is W, this W. The final velocity is 0. So average velocity will be equal to W plus 0 over 2. That is the average velocity. And total angle moved through will be equal to 2 pi N1. Remember, we are talking about after it has stopped. So W now will be equal to, and we know T, W over 2T, that is the time, this one, is equal to 2 pi N1. So W equals to 4 pi N1 over T1. So with this, we can bring this into this place. And we know our V2, our V is also equal to this one times R. So if we know the radius of this, we just put it here. So by the time you calculate everything, we'll be able to get I. When we put all the right figures, we'll be able to get our I. So that is all. Very simple and straightforward. You can see very few steps. But just put, and I like using energy equation when I'm working on anything physics, unless it will be too long. I like using energy. So you can see with this, energy equation has given us all the necessary requirements we are looking for. So